Okay? I think that'll kind of wash out as you use circuits more and more and draw the circuits and use circuit diagrams. You'll get used to the fact that those wires are perfect conductors when we draw them in a circuit. Okay, so what we need to do now is take a look at parallel circuits just a little bit more, and then we're going to talk about how we combine devices when they're in series or when they're in parallel. Okay, so we've talked about how the current moves through the circuit. It gets to a junction, right, a fork in the road. It splits. Some takes one path to the low end of the battery. Some takes another path. Okay, so the brightness of each bulb in this circuit, how does it compare to the brightness of the bulb in the one up here? I've already used the same symbol. Oh well, let's see what happens. Up here, this one bulb circuit hooked up to this battery versus this two bulb circuit hooked up to the battery. How do you think the brightness will compare? Okay, here are my two bulbs, equal brightness. I'm going to take this one out. Ready? How did the other one change? Didn't really change, did it? So we took this out. We got the same as, we basically made it into a one bulb circuit, right? We turn this one, we hook this one back up. This one doesn't change, but what does change? The current through the battery, right? Because we are still getting, obviously, we're still getting I1 through the single bulb here. And now we're still getting I1 through here, but we're also getting an I1 through here. So the current through the battery, doubled when we connected the second light bulb. We okay with that? Yes. Because let's take a look at our Ohm's law equation. V equals IR. So the voltage that we're supplying from the battery stayed the same, but what changed is the resistance. We've added a second path for the charges to get from the positive terminal of the battery to the second terminal of the battery. So we've lowered the overall resistance of the circuit. I know it seems counterintuitive. We added a resistor to our circuit, but because we added it in parallel, it lowered the resistance of the circuit. Think about the charges fighting their way from the positive terminal to the negative terminal of the battery. They come out the positive side. They come here. If this is not here, if it's a one bulb circuit, they all have to fight their way through this to get to the other side. Now we hook up a second path. They come here, half can fight their way through this path, half can come over here and fight their way. It's like going to the supermarket and there's only one line open, right? That's this circuit. Everybody has to check out through the same line. Then they open up a second checkout. Half the people go here, half go here, and twice as many people get out of the store. Matt?
I guess what's confusing me is that the situations are kind of different because in the series circuits, you're removing a light bulb, but the circuit's still complete, right? In this one, you're removing a light bulb and that portion of the circuit. What if you just remove the light bulb from the parallel circuit and completed that? So just move the resistor from the second pathway. How would that affect it?
Yeah, so you're saying that what the circuit really looks like is this. Oops. I've blown right through our break, haven't I? This was just, we were so engrossed with current and resistance. I'll give you a few minutes here, hold on. So we've got our light bulb here, right? And we remove the second one. So what we've got is a couple of wires dangling out here. Is that right? Is that what's bothering you?
Yeah. What if you just, like, what if you removed the light bulb but you completed that, those wires?
Oh,
How would that affect the current?
that's an interesting question. We'll talk about that in a minute. First, this. So this is really what we have, right? I removed the light bulb, and these dangling wires over here, what do? Because they're not connected, they don't do anything, right? It's like having a hose. You know, you've got a hose, and then you have a branch, and two hoses come off. And the water can flow through both sides as long as there's a path for them to flow, right? But if this one is blocked, because electrons, they can't go off the end of the wire, right? They're in the wire, they have to move in the wire. If there's no connection here, it's like putting a cap on the end of a hose. The water can't flow anymore through here, and so all the water will flow this way. It's like removing it all the way back here. This hanging wire doesn't do anything. Does that help a little bit? Okay, let's take a short break. Stretch your legs a little bit, and then we'll talk some more about current and resistance. So, let's talk now about resistors in series first, and then resistors in parallel. We've already got a little bit of a feel for this, right, from the light bulb demonstration. So in the first case, what did we do? We had two bulbs in series. That was this top one. We got a certain current to flow. We took one of those bulbs out. We got a larger current to flow. And then we introduced Ohm's law, which says if the voltage is the same and we got more current, then we must have a smaller resistance in this case. So one resistor acts as a small resistance. Two of them in series acts as a bigger resistance. So it's as if we are adding them together. Right? The current first had to fight its way through the first resistor. Then it encounters a second one. It has to fight its way through. So we're adding the effects of the resistance. You see that? So for resistors in series, but we call this the equivalent resistance. And what I mean by that is that if we had a battery driving a bunch of resistors in series, R1, R2, R3, and we wanted to replace all of those with one resistor that was equivalent, that would give us the same current coming out of the battery and the same total power dissipated, things like that. Which, same battery here, what equivalent resistance would we use? And it turns out you just add them up.